All right, folks, last unit of Chem 20, we are going to be looking at gases. With respect to carrying through to Chem 30, chemistry, or not chemistry 20, the gases unit really doesn't carry through into chemistry 30. So still important for you to learn it. It is still technically part of the program of studies. However, if you are still struggling with some of the solutions, acids, bases, or stoichiometry, and you are planning on taking chemistry 30, I would probably suggest that you spend more time on those and maybe just kind of quickly look through the gases unit just to kind of see what it's about. You're generally going to find the videos within this unit are quite short. Compared to the other unit, it's probably the simplest of all. It does have formulas, however, we have always given you guys a formula sheet for the gases unit because it doesn't carry through into chemistry 30. So it, to an extent, makes the calculations a little bit easier because you're generally just plugging into an equation and solving for it. Obviously, you do have to be able to rearrange that equation, but for most of you, you've already taken math, you did this in Science 10, so it's not really too hard of a thing, okay? So today's lesson, we are basically just going to kind of introduce you to gases and talk about some of their physical properties. You're going to see that as we go through the unit. It's kind of half theory and half math. So we talk about all these properties at the start of the unit, and then the further we go through the unit, you see that you are actually able to explain why all of these properties exist, okay? So first property we have for gas is that gases are compressible, right? So we can take a large volume of gas and we can compress it or squeeze it so that it occupies a much smaller volume, right? If you think about like your propane tank for your barbecue, there's a lot of gas in there, but it really doesn't occupy a huge amount of space. But that's because it's under pressure, so we force those gas molecules together. Okay, next property is that gases expand as the temperature is increased, right? If this has ever happened to you, like especially if your birthday's in the winter, you know, you're inside your house, you blow up your balloons, you take them outside your house, and then like you go back 5 minutes later and they've shrunk down and they're these not very full balloons, right? And that's because it's significantly colder, so they shrunk down in size. Or vice versa, if you like blew them up inside, it was a super hot day and you put them outside afterwards, you might find that if you go back later, some of them might have popped because they just got too big, or some of them might just be bigger. All right, next property is gases have low resistance to flow. So you don't generally think of being able to pour a gas because gases tend to be colorless. But similar to a liquid, you definitely can pour a gas. I remember seeing some video on YouTube a long time ago where someone had like a little boat in a pond, like a little aquarium pond, and they had like a gas in a container and they poured it, and then you just see that the boat starts to sink because the gas was actually very heavy. So you could see that they were pouring it. So it was an opportunity to see a colorless gas being poured. Okay, gases have much lower densities than solids or liquids, right? So density is mass per volume. Okay, we find solids tend to be the most dense, liquids kind of next, and gases are the least dense. Next property is that gases mix evenly and completely when put in the same container. So they are all miscible. So this is different than liquids, right? I always talk about like salad dressing as that classic example because you always have that water and oil separation in any type of like vinaigrette salad dressing. And even if you shake really hard, there's still going to be that separation. But what you find with gases is it doesn't matter if one is polar and one isn't, right? And for liquids that mattered. But when it comes to gases, it doesn't matter what kind of intermolecular forces they have, they're all going to mix evenly. Okay, gases can be described as fluids that have no shape or volume of their own. They will take on whatever shape and volume the container into which they are placed contains. Okay, so they could be a huge volume, they could be a small volume, they can have all different types of shapes. So all of these properties of gases are macroscopic, which means they can be directly observed. We tend to divide properties into macroscopic and microscopic. Microscopic means we can't actually see it, unless generally we have the use of like a microscope or something, right? Whereas macroscopic means I don't need anything special to see it. I can just look at it and I will be able to see it. So this brings us to our kinetic molecular theory. Okay, we use this theory to basically explain all of those characteristics we just talked about on the previous page. So this is a theory, it is not a law. So theory means it supports the evidence that we have, it works in the majority of cases. We haven't officially been able to confirm it in every single way, which is why it is not a law. And you will see why that is the further we go into the unit. You will see that there are some situations where gases don't do what they are supposed to do, okay? So to create the kinetic molecular theory, scientists basically defined a hypothetical substance called an ideal gas. So you're going to find throughout the unit we talk about ideal versus real gases. So a real gas is a real gas that's going to do what real gases do. An ideal gas is a gas that does everything that theoretically it is supposed to do, okay? So all the equations and theories we are going to talk about all involve ideal gases. So there will definitely be some real life situations that don't apply to this particular law, okay? We do find that there are modifications of the theory that can account for some of this non-ideal behavior. And you'll see if you take a first-year chemistry course, you'll start talking about van der Waals equation. And you'll see how we have some additional variables that we can use so that that equation does apply. But when we're in Chem 20, we're really only focusing on those ideal gases. So to start with, we have to define what is an ideal gas, okay? So in an ideal gas, your gas molecules are in constant random motion. They move in straight lines until they collide with something else. Okay, that something else can either be another molecule, at which point, kind of like pool balls on a table, when they collide with each other, they both bounce off in opposite directions. Or it could be that they hit the walls of the container. Okay, so they're going to move in straight lines, they hit something, they bounce, and they go in another straight line. They hit something else, and then they go somewhere else, okay? But always straight lines, and they only change directions when they collide with something. Okay, next thing is that the molecules of an ideal gas are point masses. Okay, so point masses means that they have mass, but they don't occupy any volume. And so this is where some of you might be like, well, but that's not true. I know that molecules do occupy space, right? And so this is where you find that some properties of an ideal gas aren't necessarily 100% true for a real gas, but that they kind of still are true, okay? The reason they're still kind of true is if you think about the actual size of a molecule, we generally measure that in terms of like picometers. They are very, very small. Think about the size of a container. Well, we're probably talking centimeters at least, right? Generally, we don't have super teeny tiny containers, otherwise we can't see anything. So why we can consider them to be point masses is the amount of space they occupy with respect to that entire container is basically nothing, right? And so that's why we can consider that to be true for real gases. And we can say, hey, they have weight, but they don't occupy space. Okay, next thing for an ideal gas is that the gas molecules interact with one another and with the walls of the container only through elastic collisions. So for those of you that have taken physics, you're familiar with elastic versus inelastic. Those of you that haven't, it's basically referring to what happens to energy, okay? In an elastic collision, energy is completely conserved. So we don't lose any energy to friction, to heat, or any other type of source. Okay, so whatever total energy our molecules go into the collision with, the total energy coming out is the same. One might have more, the other one might have less, but the total is going to be the same. So this may not, well, actually is not technically true for real gases. However, what we tend to find is that real gases collide with each other so infrequently in a container that that's why we can more or less consider it to be true. Okay, next thing is that the molecules do not exert attractive or repulsive forces on one another. Okay, so again, we know that this technically isn't really true because at minimum they would have London dispersion forces and there would be some attraction. But again, this is true for the same reason as the elastic collisions. and that is that they come by each other so infrequently that the opportunity for that attraction or repulsion to develop isn't really existent. So we can consider that to be true for real gases, okay? So I think that kind of concludes your introduction. So kinetic molecular theory basically involves that we have this ideal gas and that it moves in straight lines, only changes directions after a collision. Collisions are all elastic. There are no attractive or repulsive forces, and they are point masses. Okay, so those are some properties you want to make sure you remember, because as we continue through the unit and we learn about different laws, we're always going to come back to the kinetic molecular theory and how we can use an ideal gas to actually explain that behavior.